Yeah, it's a pleasure to be with you all here today. The title of my talk is The Sound of Architecture by Means of Virtual Acoustics. In other words, like Christopher was explaining, to tell you about some pretty cool, interesting technology that we have been researching and developing for the past few years for simulating acoustics of spaces and experiencing the simulation results. Okay, I'll just dive right ahead. This is the outline of my talk. I'll first just give a brief introduction to sound and acoustics in the built environment in general, and mention some of the problems that we're facing in that field. I guess this is somewhat preaching to the choir here, but nevertheless. Then go on to talk about virtual acoustics or acoustic simulations. I sort of use these terms rather interchangeably, and give sort of a brief basic introduction to the field, and then go on to talk about some selected research topics that I and we have been doing in this field. And finally, round it up with a couple of case studies where we've actually been using this technology in practice. But before I dive into it, briefly about myself. So as already explained, I have a PhD in acoustical engineering from DTU. I also did it with my PhD in collaboration with an architect firm called Henning Larsen. Before my PhD, I was an acoustic consultant in an engineering consulting firm for quite a few years. And actually, before I came into the world of acoustics, I was a software engineer in a telecom company. And these days, I am working at Treble Technologies, which is a startup we have founded here in Reykjavik, where we are developing software for simulating acoustics and doing virtual acoustics. And I also hold a part-time research position here at the University of Iceland. I'm sitting here in the acoustics labs today. Doing some research in acoustics. Okay, so there has been a plethora of research done that shows that acoustics and soundscapes have a major influence on the health and well-being and productivity of building users. For example, in open plan offices, research shows that when the acoustics are good, the productivity goes up and people will feel less stressed and so on. But at the same time, one survey after another is showing that something like 70% of people are actually unhappy about their sound environments in office buildings. In educational buildings, when the acoustics are good, then students perform better, the teachers are less stressed, the voice health of the teacher is better, and students even judge their peers and their teachers more positively. In healthcare, we see when the acoustics are good, then pain medication usage goes down, less cases of rehospitalization, faster healing and recovery, and so on. Outdoor noise, which is maybe a bit out of scope here today, but nevertheless a major problem, of course, too. The World Health Organization is saying that something like 1 million healthy life years are lost every year just in Western Europe due to noise, and that environmental noise is the second most harmful environmental hazard just after bad air quality. And then sort of honing in on what we're talking about here mostly today, although this certainly is not a small room, but music spaces, concert halls are obviously important to have good acoustics in those too. This is a hall called Harpa, which is just here around the corner in Reykjavik, designed by Henning Larsen. And small rooms, control rooms, critical listening spaces, obviously important to have good acoustics. And also mentioned car cabins, for example. It's another small space where acoustics matter. All right, but when we set out to start this research work some 5 years ago, we didn't actually set out to make faster simulation algorithms or more precise simulations or something like that, even though our work kind of led us there. But we sort of fundamentally rather tried to ask ourselves, can we do something? Can we develop some digital technology or some methods that can make sound a more integral part of building design, such that we have sound influencing the design from the earliest sketches and throughout the whole process, and end up sort of shaping spaces, doing space planning, selecting materials, all with sound in mind. This led us to virtual acoustics, and I say here that we are developing a new way of dealing with sound in building design. And our sort of long-term vision is that we want sound to be an integral part of the 3D models that the building industry, the architects, the engineers, and stakeholders, and so on are using every day, such that you not only see how your design looks, but you also hear how it sounds at the same time. And ideally, this should be some sort of interactive experience where you can change the design and experience it on the fly. But if I just take a step back here, from the long-term future vision, then this is a slide that sort of illustrates the process regarding acoustic simulations. We start with some input data, 3D geometry model of the geometry in question, along with some description of the acoustic properties of the surfaces in the room and the sound sources in the room. This information is then fed to a simulation algorithm that computes how sound propagates in the room and the resulting acoustics. And this algorithm then outputs some results. These can be graphs and numbers that indicate the acoustic quality or the acoustic comfort of the space. You can visualize the sound field, and what's typically called oralization. We can listen to the simulated space. And I myself have been mostly working here at the simulation part itself, trying to improve the accuracy, the flexibility, the speed, and so on. And also a lot here on this listening part, trying to create the system that allows us to couple the visual model with the sound model and do this interactive, immersive experience of a space. And I'll talk about both aspects today, but first starting here with the simulation methods themselves. So throughout the years, there have been many different methods proposed to simulate acoustics, but usually these are divided into one of these two categories. We have the geometrical methods here on the right and the wave-based methods on the left. In geometrical acoustics, these are ray tracing, image source method, beam tracing, and so on. Here we do a lot of approximations or simplifications regarding the wave propagation simulation itself, which has the benefit of making the computational process much lighter, i.e. faster simulations. But the drawback is that the accuracy can be low, and particularly in cases where wave phenomena such as diffraction and interference is prominent. And this, of course, happens more in the lower mid-frequency range of the spectrum and in smaller and medium-sized rooms. Although there's some interesting research, for example, in even large spaces like concert halls where wave effects occur quite above the Schroeder frequency. And then here on the left, we have the wave-based methods, where there they have sort of pretty much the opposite pros and cons. There we do use numerical methods, numerical discretization techniques to solve the physics equations that actually describe wave motion, and that they in principle can be very accurate because we don't make any approximation on the wave simulation itself. But the drawback is that the computational costs can be quite heavy. So I have been mostly working here in the wave-based part of the world, trying to make them faster, more flexible, more accurate, and so on. And leading into a few selected research topics on that. First has to do with sort of advanced numerical modeling of room acoustics. So here we have been taking cutting-edge numerical methods and adapting them to room acoustics. In particular, we've been working with a numerical method called the discontinuous Galerkin finite element method. We've been working with mathematicians both in DTU and also in EPFL in Switzerland. And we basically approached them and said, what is the best method if these are sort of our list of requirements? We want fast simulations, we want to be able to simulate complex rooms and so on. What do you recommend we use? And they pointed us to this numerical method, which is very attractive for the problem because it has these three main features here. First being geometric flexibility. We can handle complex shaped rooms and detailed geometric features. Second being its suitability for parallel computing. So as opposed to when you have a normal finite element mesh or simulation, then each element in the mesh is kind of linked together, which makes the parallelization a bit difficult. But in a discontinuous formulation, each element on the mesh is sort of independent of each other, which means we can solve them in parallel. And then the last feature here is something called high order accuracy. I won't go into the details of what that means, but long story short, it means more cost efficient or faster simulations. So here's just one comparison when we compare a low order typical finite element method simulation against a high order simulation for a classroom sized room. And we record the runtime when using a particular computer as we increase the frequency range of the simulation. And we see here that the runtime grows sooner when we use the low order method compared to the high order method. For example, if we want to simulate this room up to 1 kilohertz, then it takes around 7.5 hours for this particular hardware we're using, and around 17 minutes with the high order method. So Yeah, when we couple then this advanced method with these advanced modern computing architectures, in particular these GPUs, which can be very useful to accelerate the simulations when you have a method that's suited for parallel computing. And the way it works briefly is that we have, this is just meant to represent like a room, just a small box-shaped room, which is then divided into subdomains, and each subdomain in the room is handled by a CPU, one single CPU core, which is linked to a GPU that has thousands of cores. And then because every element here is independent of each other, we can solve them in parallel on the GPU, and very minimal communication between CPU cores has to take place. We've spent a lot of effort researching how to best implement and optimize these algorithms to work with these hardware. And we've gotten very good results where we can accelerate the simulations by something like 3 orders of magnitude when using GPUs over CPU architectures, or two to three, let's say. And just to make these numbers a bit more tangible, here we simulate fairly large rooms, auditorium, 5,000 cubic meter, and concert hall, 20,000 cubic meter, up to and around maybe up to 1200 hertz or something like that, where we have good, accurate results. And we can, when we used 8 GPUs, we could simulate the auditorium in around 1 hour. We only had 12 GPUs to play with, so we could get the concert hall in 3 hours in this case. And this is obviously far above the Schroeder frequency here. Okay, another thing we've spent a lot of effort on is material modeling. So as we all know, the acoustics of rooms are very influenced by the surface properties, or the acoustic properties of the surfaces. And then therefore it makes sense that it's important to model those precisely when we do acoustic simulations. And in particular, we zoomed in on these porous materials, you know, your typical mineral wool, fiberglass, etc., these wall panels, the suspended ceiling here, furnishing, and so on. And in wave-based simulations, the traditional approach to model room surfaces is to employ what's called a local reaction assumption. That means that we assume that the interaction between the pressure and the particle velocity at the boundary is an entirely local phenomenon. But in reality, for most room surfaces, it is not a local phenomenon, but instead you have wave propagation along the surface, which is typically called extended reaction. And we developed a way to model this extended reaction behavior of porous materials, or in other words, to capture sort of the full physics of these porous materials in this time domain DGFM scheme that we are working with. And the way we do it is that we model the sound propagation inside the porous material using an equivalent fluid model, and couple this with the air domain simulation. So this is meant to replicate like the suspended ceiling case here. We did some validation studies of this. We have a sound source here emitting a wave at different incidence angles, hitting a suspended porous material and being reflected back. And then when we look at the pressure at the receiver positions for these different incidence angles, when we compare the equivalent fluid model approach to the typical local reaction approach, and these two are compared against an analytic reference solution, so sort of a ground truth case here, then we see that for the normal incidence case, there is a very good match between all three. But when we go to higher incidence angles, and indeed this extended reaction behavior starts to take place, then the local reaction assumption totally breaks down, whereas the extended reaction or the equivalent fluid model approach matches well with the reference solution. We also did some experimental validation. This is from a previous study undertaken at DTU by Kristrún Gunnarsdóttir and co-authors. We have a sound source here and a receiver here, and wave coming in at different incidence angles, hitting a suspended porous material. And when we look at the transfer functions between the source and the receiver, then we see that the equivalent fluid model gives a better match to the measured data compared to the local reaction approach. Still some room for improvement, I will say. Also some uncertainty, of course, associated with the measurements and so on, but a step in the right direction. Okay, and the last topic I wanted to talk about is this interactive virtual acoustics, or this idea of creating these audiovisual virtual renderings of spaces. And we have devised a system to do this. For us, it was very important to use highly accurate room acoustic simulations. And this means that we cannot really use real-time simulations, because even if we would use the most powerful hardware in the world and the most advanced methods, If you want high level of accuracy, then it cannot really be done in real time. So instead, we do a sort of a pre-computation stage where we pre-simulate the acoustics of a room in a grid, essentially across the room, and we embed spatial information into the simulated impulse responses using ambisonics. And then during runtime, when the listener is walking around the space, he's sort of followed around by this virtual loudspeaker array. And then there's a real-time audio processor that decodes the sound field depending on where you're standing in the room, what the orientation is, and does some interpolation between points and so on. And this is then fed along with the visuals to the VR headset. We did a lot of tests with this system. Here's just one example where we did a localization performance test. So we asked people to identify where sound is coming from in space. We compared first versus second order ambisonics in the spatial encoding part of the system. We presented the stimuli under different conditions, presenting only the audio, presenting the audio but having head movement using head-tracked headphones, presenting the audio and the visuals only, and then presenting everything together. We did this for 3 different rooms with different acoustic conditions. And what we see here is that second order ambisonics is better than first order ambisonics. That's no surprise. Secondly, we see that by allowing head movement in the listening experience, we greatly improve the localization performance. This is perhaps also not so surprising. We know that when we're listening in real life, then we sort of do these micro movements of the head to better localize sound and so on. Also interesting to see that by just adding the visuals of the room together with the sound, then we improve localization performance. So this implies that some sort of holistic experience of the space is better than just presenting the audio. And then if we do allow everything, then we actually get very good localization performance. Okay, couple of case studies here. First, just a basic simulation versus measurement scenario. Small room here, fairly rigid room, also just box shaped, but we have a porous material here on one end of the room, tried with 2 different porous materials, and we see pretty good match between the measured and simulated frequency responses in the room. Then regarding this virtual reality stuff, it's usually a lot of fun to allow people to try these things. In this case, I wanted to tell you about here is this is an old office building in Copenhagen. We did this together with Henning Larsen architects. They were supposed to be completely renovated the building and changing it from the closed style, old style offices to open plan offices. And the client was sort of fairly concerned about the acoustics of or the sound environment of the open plan offices. So we did a virtual mock-up of a typical open plan office in the building, and I will show you a video from it. In the video, you can see the user walking around the space, and with a click of a button, he can sort of switch on and off various aspects of the acoustic treatment. For example, the acoustic ceiling or the dividers between workstations and these glass windows that we put, or glass dividers we put here, and carpet on the floor or hard floor, and so on. I should say before I play it that my experience, I have somewhat mixed experience with playing these types of demos over Zoom or Teams. Sometimes the audio can be a bit low, for example, but I hope it goes through to you all. And if not, then you can go to YouTube and just write Treble Virtual Acoustics and find it there. But at least you should see roughly the idea here, what this is about. Let's try it.
Nej, det var faktisk logistikken, der var det allerstørste.
For I rev bygninger ned på Amager og sendte murstenene til Nordjylland og fik
ja,
dem
det er min skyld. Vi udviklede...
Okay, so that's the idea at least. Here's another case I wanted to mention. This is still not really been made public, so I won't tell you about who we did it with and where it's in the world and so on. But anyway, it's just a pretty interesting space, I will say, from an acoustical point of view. It's like this cylindrical shape, a lot of concrete and so on. So obviously challenging from an acoustical point of view and challenging to model too. We did a wave-based model of this room. Well, a wave geometric hybrid, actually. That's usually what we do. We simulate the low and mid frequencies with wave-based and then the very highest frequencies with the geometrical method. And here you can see the initial model and the computational mesh and then some results here. So it proved, for example, beneficial to view these animations of sound field propagation in the room. We could see here how sound is sort of traveling along these, also spinning essentially along these curved surfaces here. We could exploit that by putting sound absorbing materials here in these pockets of the space, where sound is essentially rounded up by the geometry. That proved to be a very effective place to put absorbing materials along with some other parts, for example, the ceiling. I can mention that using our cloud-based simulation algorithms, we simulated this space in up to around 1 kilohertz in about 20 minutes using one GPU. And we did the same space in ComSol, which is a well-known multi-physics finite element solver, which does not use the cloud, but just your desktop computer, and it took 72 hours to do the same simulations. Some speed-ups have been achieved. And we also tried simulating the low frequency range with geometrical acoustics, and we saw very big differences between what the wave-based and the geometrical was predicting for this space. The space hasn't been built yet, so we don't have ground truth to compare against, but I very much would like to argue that the wave-based is closer to the real thing. This space is very well suited for wave-based simulations, being curved and small and so on. Yeah, and that's essentially it for my talk. I just wanted to mention that so we in Treble, we're fairly, even though the research dates back some years, then the company is quite young, but we're planning to release some of these products maybe around next year to allow people to do wave-based simulations in the cloud and do these virtual renderings of buildings and so on. But in the meantime, if anyone out there is interested in some of this stuff, then by all means reach out and we can do some cool and fun stuff together. We're very interested in the studio space and the small room field. So if someone is doing something fun there, then by all means just feel free to reach out. And thank you very much for listening. I'll be happy to answer any questions that you might have.